for the introduction. So I'm going to talk about, I'm going to tell you a story, actually, that will segue into my current research. And I'll try to keep it half an hour, but
I will give you a little signal when you have a 2-minute.
All right, so first, because I think the audience here is quite general, all over the place, we do a little quick intro to vehicles, traffic, emission, air pollution, environmental justice concerns, and then we'll start with the story. So first, the concentration of emissions from vehicles are higher, closer to roads. Not surprising, but you know, there's this wonderful paper that quantified all these things. It's a meta-analysis, and it was actually done by Dr. Alex Turner, who was my sat across from me during graduate school at Davis. So, and you can note a few things here, though, that are kind of interesting. One, you can see there's a lot of different emissions that come out of vehicles, and they actually drop off pretty quickly. So within a few hundred meters. So that really, we're going to talk a lot today about near road, people who live near roads and pollution near roads. And so we're talking within a few hundred meters. This is primary vehicle emissions. The emissions that come out of the tailpipe also mix in the atmosphere, react with various other pollutants, sunlight, and form secondary air pollution. So like smoke, which is not what we're going to talk about today. Vehicles are responsible for the majority of air pollution in most places. These air pollutant emissions, specifically the ones from vehicle traffic, are also known to cause all sorts of terrible health outcomes. And some of these relationships have been found to be causal over time, some are more suggestive. The Health Effects Institute is a nonprofit organization jointly funded by the petroleum and vehicle industry and the US EPA. And they conduct research studies on the health impacts of vehicle traffic. So I'm not going to list them all, but basically most diseases you could get can be caused by exposure to vehicle emissions. And we also know that people of color, people with lower incomes are often disproportionately exposed to pollution and waste in general. There's, sort of this landmark study back in the 80s that looked at the siting of toxic waste sites and the communities around those. There's also been newer studies looking at just who's most exposed to air pollution, and there's been there's hundreds of these studies of specific places. If you look at who lives next to port complexes or busy freeways or other things, these studies universally follow that. It's often a lower income community, a community of color. So we know these sort of environmental justice issues and equity concerns have been known for decades. They're widespread. So that's just a super quick background. Cars cause pollution. The pollution is closer to the road. There's more. It's terrible for you. It kills lots of people, and the people who live near roads are often have a lower income or community of color. So, okay, so part 2: a fake scientist, an agency cover-up, and a ridiculous statement by a public official. And this is how I started studying who lives near roads. So when I finished my PhD out in Davis, California, I moved to Santa Monica. And I worked for the Natural Resources Defense Council as a science fellow studying air pollution and vehicle traffic. It was an amazing gig. The office is literally 1 block off the beach right here, right next to Pier, and have a surfboard rack and everything in there. It's a nice place to land. And one of the things that happened the first couple of weeks working there was this scandal. So what happened was a scientist, called himself a scientist, working for the California Air Resources Board, developing a rule to reduce to a new rule that would further control emissions from diesel trucks in the state of California. The Air Resources Board is like a division of the California EPA, which is about the size of US EPA, massive institution. And they proposed these really tight new regulations that would require some different retrofits to vehicles in the existing fleet. And the trucking industry, right, it's huge in California. The ports of LA and Long Beach are where most stuff you buy comes into the US from. It goes all through the country. There's big port complexes in the Bay Area as well. And turns out this employee didn't actually have a PhD from UC as they claimed to have. And furthermore, that many mistakes were made in the analysis behind the rule making. So the Air Resource Board sort of covered this up for a while, saying like, well, the rules still get, and these rules take years and years of public comment involved. So, you know, okay, we have a troublesome employee, but you know, it's still okay. Well, the more digging, you know, there were some errors and stuff. So what happened was ultimately, you see, there's just some random headlines out of the news. They ended up delaying the rule and then just ditching it altogether instead of trying to fix it. And that's where NREC and my new position there was, I mean, fine, they screwed up. There was mistakes, some fraud, but can't we just fix the rule? And so there was the, okay, well, we'll delay, they'll fix it, you know, they'll eventually adopt it and now have a new rule. But the communities we were working with in Los Angeles were especially upset because this wasn't just a let's reduce diesel emissions, you know, it would improve public health, but this is a huge environmental justice and equity concern, right? People who live around the ports of LA and Long Beach, along this picture in the back of the 710 freeway, hundreds of thousands of diesel trucks every day, right? They have huge impacts. And so this rule to them wasn't just, you know, okay, someone made a mistake, but now we're paying the price. So this became this big environmental justice issue. And a high-level public servant in the state said in a call with us at NRC and the lawyers I worked with, I worked with the litigation team, so it's the scientists, the lawyers, said, but, you know, rich people live by freeways too. So this isn't some, don't make this a big environmental justice issue, right? Everyone in LA lives next to the freeways. And so that led to us thinking, well, who does live near highways? I mean, of course, some rich people live near the highways, but certainly more lower income people who are living near highways. Like in LA, we know this because we live here, we work with these communities and everyone knows it. But more generally, yeah, true is that. And you know, the questions from the people I was working with at NRCU were, well, we can certainly quantify this, right? Of course we can. This isn't terribly difficult to figure out. So we, you know, we set out on a mission to figure out how many people live near roadways, how close is too close, and then who are they? That's what I went about doing for the next year or so. We started in California and started compiling the data. Figured, well, I mean, it's like a little amount more work once we develop the codes and all the stuff to just do the whole country. So that's what we did, and that's what I'm going to talk about. And so this, you know, person who screwed up this analysis, lied about their credentials, and you know, caused this whole thing led to this investigation or this line of research that I've kind of stuck with for the last 10, 12, 15 years, however long it's been. So the approach here, and so I'm going to talk a bit now just about what I've done in the past, and then I'm going to show some newer stuff that expands on this. But initially, what we sought out to do was identify high volume roads, identify an area around them that is an area of concern, and then add up the, you know, the population that lives within that region and look at who they are. So how many people, demographic information, stuff like that. And then we also have this other way of looking at which we call traffic density, which is a survey for emission exposure. I'll talk about that a little more in a second. So we started with, we needed traffic data. And the US is the only country in the world, it turns out, at least I'm aware of, because I've been tasked with trying to find data for other places, that has a national data set. It's available every year. It takes a few years before it comes out for like the current year, but of the traffic volume estimates on every single roadway from sort of with the exception of low volume local streets, everything else is on there. So, you know, the Colchester Avenue here would be in this data set. Most all streets in downtown Burlington, but like cul-de-sacs and some smaller suburban stuff wouldn't be in it. So it's a massive data set. And it has the traffic volume for light duty vehicles, medium duty vehicles, and heavy duty vehicles. It's based on a sampling approach. If those little black pneumatic tubes you see thrown across the street, those are moved around in a kind of randomized fashion. It's a stratified sampling scheme, goes into the model, and they predict this. So this is what we used as our traffic data. We actually had to do some additional modeling to fill in the medium duty and heavy duty vehicle traffic because that sampling occurs in a sort of less frequent way. I'm not going to get into details though because we'll run out of time. But this is kind of what it looks like. So we have this wonderful detailed data and has AADT is average annual daily traffic. So traffic volume. So we started with this proximity method. We drew buffers. Weren't sure how close to close, so we drew a whole bunch of buffers, 100 to 500 meters out. We picked that range based on that first chart I showed you that looked at how the emissions kind of trail off after a few hundred meters. And we also based it on looking at the health literature, and that basically the health impacts have been found within a few hundred meters, and generally with roads that have more than 10,000 vehicles per day. So we chose 25,000 vehicles per day as sort of a more conservative limit for where you might expect health impacts. So we went and added up the population that lives in all of these buffers for each of these traffic thresholds. And these are all regions where you can expect to have elevated risk of negative health outcomes. We intersected this with census data. That's where the population data came with, and then we made some subtools. We'll show that in a second. The other thing we did, we had this traffic data to facilitate a more robust sort of equity analysis. We had all these roadways. We we estimate something we call traffic density, where we take each roadway segment that intersects a census block, and we add up the vehicle miles traveled on every roadway length. So you take the AADT, the average annual daily traffic, multiply times the length of the segment, right? And that's the total vehicle miles traveled. And then we add up all the segments within that block. And then we also include the segments in a buffer around that block. Because if there was a big highway right along the edge of this census block, well, those emissions would obviously impact you if you were living in there. So that's why we have a buffer too. So we take all that traffic volume and we divide it by the land area of the block. And that we call traffic density. And this is kind of what it looks like. So this is downtown Denver. You can see all the little census blocks. It's very dense there. And we have these estimates of traffic density. So it's vehicles kilometer travel per kilometer square. Okay, so results. Well, about 25% of the population lives too close to a busy roadway. About 80 million people live within 500 meters of road on 25,000 AADT. That's busier than pretty much any road in Vermont. But you know, parts of the interstate have that volume, maybe Shell Run Road or busy get. And right, this is the average annual daily traffic. So weekends, weekdays, whole year. So these are really busy roads. 25% of the population is really close to them. You can see it's a much bigger share of the population in some states like California, and you know, less in New England and other places where you have more dispersed population. This population is, like other studies have hinted at that have looked at specific places, overwhelmingly more likely to have a lower income and to have a larger share of people of color. So we, on this plot here, we're looking at the traffic volume on the x-axis and the portion, the percent of the population that is non-white. We have it broken out by every race ethnicity, but to summarize, have it this way here on the y-axis, and you can see as you move towards higher traffic volumes, the share of the population who is not white increases, and also as you move closer to the road, so from 500 meters to 100 meters, that it's a similar increase. So one way to look at it. Another way to look at it is we looked at the ratio of the share of, in this case, the non-white population living within the buffered area along roadways to the demographics of the surrounding county, right? So it's a ratio. So a number greater than 1 means that, in this case, the non-white population is overrepresented in that near roadway area. And if we did slightly different with income, but we looked at the percent difference in income between living in that near roadway area and the surrounding county. And we tried to look at it relative to the county to normalize for the fact that, you know, obviously incomes and the demographics of different regions of the country are a lot different. We also use that traffic density number to do a similar analysis. Traffic density is kind of cool because it's a continuous measure. We have a value for every census block in the country. There's over 3 million of them, 10 million, something, 8 million. My PhD student, Brittany, who I forgot to introduce on the slides again, she's one that does all these, a lot of the newer stuff we're seeing here and has that number, but it's a huge amount. But we have value from the very most rural census blocks to the most urban ones in like Manhattan. So it's a continuous set, and we can look here and see that as traffic density increases, these are deciles. So we took the census block, sorting from lowest traffic density to highest, put them into 10 equal-sized bins, and then looked at the characteristics of the population falling in those bins. In this case, we're just summarizing here the non-white population share. So it goes from about 16% in the lowest traffic areas to 57 to 60% or so up in the with the highest traffic densities. And LDV is light duty vehicle, medium duty vehicle, heavy duty vehicle. Similar trends. And right, this is a huge range, and that it is just monotonically increasing from even out here, which are super rural areas, just a little bit more traffic. There's just a little bit of this share of non-white population. So something very similar. Income increases for a little bit, and then just declines until the very end. And right, when you're in these high density areas, these are large cities and incomes are higher. It doesn't mean that you're not struggling because you need a lot more money to live in some of these places. But so when we, so both sets of data are showing us a similar thing. And it's pretty astonishing how consistent this is and the magnitude of the change. We also looked at another one. We took those plots, you can imagine. This is for the nation as a whole. We plotted the data, just scatter plot, you can imagine, XY of each block's demographic profile and traffic density. We fit regression lines through it for every county. And we report on this map the slope or the coefficient estimate, or which would be the slope of that line if we were to fit it through. And so a larger slope is a larger amount of this disparity in exposure to traffic, which is a proxy for exposure to emissions. So then here in the red map, the darker red colors are showing a larger slope, right? So there's a stronger relationship between increasing traffic density and an increasing share of non-white population living in that block. So it's done on a county by county basis. And you can see that almost every county in the country, we see this type of trend. And on the right, it's the same thing, but with income. And there's a few exceptions. And if you squint, there's a few blues in here. But even here in Vermont, we see the same thing as we see that in California or other places with more traffic and busier roads. So it's pretty universal. This type of inequity and exposure to emissions is everywhere you look. Well, So that is what been working on for the last 10 or so years. We had an original paper about 10 or 12 years ago when I was just finishing up at NRDC. Brittany, my current PhD student, and I have worked on an update to that. That's been funded by the Environmental Defense Fund. Those were the data I was just showing you. Now what we're doing with our current work, this graphic was just generated this week, is we're taking the traffic data we have. We're using a vehicle emission model called MOVES, which the EPA produces to model the emissions for every single road length in the country for all vehicle traffic. And this map right here is kind of showing the results of that. So this is NO2. So it's NO2 density. It's not a concentration because we're not using any sort of air pollution constant, any atmospheric dispersion models or anything like that right now. But we're taking the same approach we use for traffic density. So we've got the quantity, right, the rate of emissions being produced by each roadway segment. We're adding them all up for each block and plus a buffer to capture the edge effects, and then dividing it by the land area to get sort of a quasi surrogate of emission concentration in each area. And so this is what it looks like for heavy duty vehicle traffic in the US. And you can see Oklahoma here. We have some sort of data or we get figured out. But like I said, there's no scales here. Like literally, this was like in the middle of the night 2 nights ago, we finally got to this step in our work. So showing it here, it's super exciting. What we're doing next though is we are currently modeling vehicle emissions, the emission factors, so gram per mile for different types of vehicles out to the year 2050. We're going to attempt to model vehicle traffic on the link level for the whole country out to 2050. And we have some population forecasts going out to about 2100. And we're going to use this to look at some future scenarios of emission exposure and different policy scenarios. Talk about that in just a sec. With this emission density data, though, we're able to basically repeat the type of analysis we were doing with the traffic density, right? So we've plotted, in this case, these bins here, these are those deciles. So we have the census blocks with the lowest emission concentrations sorted to the highest, and then we look at the population characteristics within each of those bins. And right, so they look very much like the traffic density plots because the emissions are just the factors multiplier on top of the traffic density, although emission rates vary from place to place based on the vehicle fleet, climate, traffic conditions, and other things that we account for. So they're a little bit different. This data also reveals what's going to become a challenge for electrification, that heavy duty trucks are responsible for a huge share of emissions. So I've highlighted the row here. And so light duty vehicles, so you can look between light duty and heavy duty vehicles, they are responsible for about the same amount of sort of quantity or share of emissions in most places, except that this amount of emissions is produced by like just a tiny fraction of the number of vehicles light duty, right? So heavy duty vehicles emit about 40 times the rate as a light duty vehicle. So it only takes a few trucks to reduce the emissions of hundreds of cars. I mean, under a certain condition, the ratio can be even greater than that. So current research, as I was explaining, is we're now forecasting all this traffic volume forward. So we've currently just been working with current data. And we're going to model future emission rates. We're going to come up with a way actually to try to estimate concentrations from the emission density. So we'll actually have a concentration of air pollutant in the air, which then will allow us to use health impact models to estimate health outcomes. That's what I'm showing on the right here. This is some of my other work that's on a city scale where we're able to do things in greater level of spatial detail. And we use, atmospheric dispersion models to actually estimate concentrations of air pollution in the air, which is the type of data we need to use health impact models. And so this is Atlanta. We estimated the change in risk of different health outcomes under some different transportation planning scenarios that the metropolitan planning organization have put together there. And then we want to use this modeling framework, get all this stuff to work. We want to create different scenarios of traffic growth and the adoption of electric vehicles over time, and to see, if we are slow to adopt electric vehicles, what are the health impacts of that? How many people will die? How many people will get cancer? Or alternatively, if we can do things quicker, how many lives are we saving? And, if these things don't happen evenly, what are the environmental justice equity implications? And there are some challenges too, like I hinted at trucks. Trucks are about a third and a growing share, the fastest growing segment of traffic in the country. And it's not very easy to electrify the trucks. So that's going to be a challenge too. So I'm right at my 30 minutes, and I just threw up a few questions here to help seed some conversation beyond any questions you might have about stuff I showed you. And I also just, so there's these, and I also do have, because I, feel bad about excluding lots of groups when I just show plots of the non-white population, but we've looked at it every which way that we could. So everything the census reports, so every demographic in the decennial census, we have basically divided against these emission density, traffic density figures. These are some more. That's what I got.